to open up for questions as well, so let's have you guys think about questions. Aubrey, are there other thoughts that you think are important to address as well?
No, I think you've got the general idea. I think we've probably stimulated you enough.
Awesome. Okay, cool. And give us just one moment. We have a wireless mic. We want to make sure to capture the audio from your questions, and we're coming at you with it right now.
And we've got quite a bit of time, by the way.
Yes.
I have to be out of here by about 9, but that's an hour from now, so Don't worry if we have to wait a few seconds for the microphone to come along.
Okay, so this is a probably predictable question you get often, which is, if things don't change in terms of funding, and Calico's doing their thing, and you're doing your thing, what is your projection of when that moment's going to be when the 12 people stand up and say, we think it's a solvable problem?
So, well, first of all, the funding is changing quite fast. The whole creation of this industry, the creation of these startups and so on, spin-outs of our projects, even 3 years ago, that just had not begun. So this is changing gratifyingly fast. So that's a really bit of good news. However, to answer your question directly, how soon are we going to get to that tipping point? Yeah, I think it could be awfully soon. You see, if we ask the question, how soon are we going to get to the therapy being available for humans, then I have to give, a terribly speculative answer. And I do give an answer. I think that, we've got a 50-50 chance of getting there in 20 years from now. 10% chance at least that it could be more than 100 years if we hit a lot of new problems, but 50% chance is quite enough to be worth fighting for, so that's all good. But we're very unlikely to get there in less than 15 years. But for the tipping point that I was talking about in terms of public opinion, the criterion that one has to evaluate is how fragile the pro-aging trance actually is right now. In other words, how tiny the amount of progress would need to be, the amount of positiveness that the experts would have to be expressing in order for the dam to break. And honestly, I am having a hard time putting a good number on that. I think that, I've thought about this a bit, obviously, but honestly, I'm terrified. It could happen next year. It could happen awfully soon. If you ask me a 50-50 probability, my best guess would be around 5 years from now. Pretty small amount of progress. And this is absolutely not to do with the funding thing you mentioned. This is because of those kinds of time frames don't really make much difference in terms of how much money is involved. So yeah, 5 years-ish, and could be a lot less.
Because you're putting like 90% on 10 years or less.
Yeah, I am. I think that it's very likely indeed, I would say yes, 90%, that within 10 years we will reach a point where it becomes essentially just a pragmatic, even from a pure mercenary vested interest perspective, funding perspective, to those gerontologists. Even though those people will still be the dinosaur basic scientist types who really aren't thinking in terms, who are spending their time making sure that they continue to be able to approve each other's grant applications. Those people, even they will come to the conclusion that it just is riskier to continue to be curmudgeonly than to tell it like it is.
We have another question over here.
Yeah, so my father's father died when he was 52 from heart disease. My dad currently is in his mid-70s and is absolutely obsessed with anti-aging culture and learning more about the science behind it. So he wants to ask, this is me, asking for him, what could you do today to extend longevity, right? Like, what is there action? What is actually actionable at this moment besides?
Yeah, and of course I get this question all the time, and it is the fattest question, because the fact is I have to tell the truth. There is nothing you can do today other than writing me a large check, and even if you do, it's probably not going to help you if you're over 70. So I have to just get people to fucking pay attention to the fact that their kids matter, and even if it's not in time for you, you'll still save a lot of lives. It won't just include your own. But yeah, fact is, there's all manner of things out there right now, very experimental. Things are, we might not be too far away from things that could actually make a bit of a difference. But what we really care about is things that make enough difference to buy you enough time to get the next thing, this thing that I call longevity escape velocity. And we're a good few years away from that.
Let's come up here.
So,
We have the mic coming right here. Thank you.
pretty loud voice. So, 2 questions. One is, how long do you think you can expand life? And the second one is, what I've heard you saying is really about stem cell implantation. And is there something else, or is it just implanting stem cells and hoping they regenerate, and then after a period of time you do it again and again?
So, certainly, first of all, I can totally take the word hope out of what you're saying. We do science, we obviously hope that our science moves faster than otherwise, but by the time it gets to you, it won't be hope anymore. So the purpose of all of these regenerative therapies, including the stem cell ones, is to repair the body in whatever way is needed, and there's lots of different types of repair that are needed. Now, the details of the implementation do vary a lot. There will be some cases where we can put cells in, and it's basically a one-off. We'll just never need to do it again, or at least not for a long, long, long time. There'll be other cases where it'll be, need to be done every couple of years, because it'll be a different kind of therapy that, with fixing a different kind of damage. And of course, that may be improved over time, either in terms of the frequency, maybe go to lower frequency, or in terms of the convenience, so like, for example, moving from surgery to an injection so that it's fine for it to be every year rather than every 10 years, things like that. Lots of these little details are case by case, and most of them are not clear yet at all. To answer the first part of your question, though, there is no limit. This comes back to the phrase I used a moment ago in response to the previous question, which I shall elaborate on because a lot of you probably haven't heard it. I coined this concept about 15 years ago called longevity escape velocity. And what it arises from is the fact that the therapies which are going to work, as I've already explained, are going to be rejuvenation therapies that do not simply slow down the rate at which the body creates damage, they actually repair pre-existing damage in the body. That means that if you take somebody's age, let's say 60, and you fix them up, then even if you're doing the fixing up rather imperfectly, you're going to buy some time. Let's suppose you do it so well that by the time they're 90, they've only got the same amount of damage that they had when they were 60, right? Because you fixed a lot of the damage, but not all of it. Now, if you think about it, the amount of damage that they had may be the same as they had when they were 60. But the type of damage won't be, because, of course, the type of damage will be the stuff that the therapies don't work on because of the imperfection. But you've had 30 years to improve the therapies. Or we have, not you. So that means that the therapies we can apply to that 90-year-old who's biologically 60 for the second time will be better ones that can actually work on some of, again, not all, but some of the damage that the first therapy didn't work on. And that means we can re-rejuvenate the same people, so that they won't be biologically 60 for the third time until they're, let's say, chronologically 150, and so on. This is what I've called longevity escape velocity, the rate at which, the minimum rate at which we need to improve the comprehensiveness, the approximation to perfection of these therapies in order to stay one step ahead of the problem and to repair damage faster than time is passing. And I believe that once we get the first generation of these therapies, the ones that I think will probably only give the first 20 or 30 years of extension of life working, those are the ones we're already working to develop, okay? Once we get those working, which is what I said I think could be 20 years from now, then we're done. We will easily be at longevity escape velocity. We will easily be able to continue to improve those therapies faster than we need.
We'll come back here in a second. Does us getting our genomic sequenced and microbiome analyzed, do those things help you understand us for when we need your therapy?
Genomic sequence is always useful for a lot of things, but I don't think it's going to be all that useful in terms of the application of these therapies. The use of genomics right now, and also epigenomics, of course, and metabolomics and proteomics, all of these very personalized data sets are very helpful right now in the development of stopgaps, in the development of drugs that kind of do a little bit, to maybe postpone this or that thing. And maybe also they will give us some insights into the shortest route towards developing therapies of the sort that we actually work on. But when the therapies exist, they will not be very important for the reasons I spelled out earlier, that we all have the same types of damage. Microbiome is a very fashionable area right now, and rightly so. It's, it's an area of biology that's very poorly understood. I don't personally believe that manipulation of the microbiome is, at least not eventually, going to play all that big a part in the panel of anti-aging therapies that we will have, largely because the microbiome consists of bacteria, which are, of course, microbes, which are, of course, dividing cells. And dividing cells are very, very much more malleable in terms of their population structure, in terms of what they do, in terms of how they behave, than anything else. So my expectation, my strong expectation, though it's only a hunch, I could be wrong, is that when we fix up all the rest of the body, the human cells, then the microbiome will come right to the extent that it needs to.
How do you expect to democratize these treatments? Right now we know that most populations can't afford what you're talking about. What's your vision there?
Yeah, so this is very important. I only briefly alluded to it earlier.
Good question.
The situation that we have today with high-tech medicine for the elderly should not be viewed as a precedent. So I want to explain why it shouldn't. And here I am not specifically singling out the USA here. You might expect me to, because I come from that far-off place called the rest of the world, of which you know not very much. But the fact is, this is not really a public-private healthcare dichotomy. Yes, it's probably worse in the private healthcare system, in the lack of access of poorer people to high-tech, expensive drugs, but it's still a problem everywhere. So I don't want to get into that. It's not the main part of the problem. The main part of the problem is that today's high-tech healthcare for the elderly doesn't work, which means that the economic arithmetic isn't there. What you have is very expensive medicines that, if you're lucky, will keep someone alive for a little bit longer in a poor state of health, consuming a lot of money. Money down the drain for very little gain. Now, that means a bunch of things. One big thing it means is that the electoral value of subsidizing that medicine is not very great. People can't really get their heads around the idea that it might be useful to spend a lot of money keeping people who are already sick and staying sick alive for a little longer. That makes sense, really. So now, consider a situation in which the medicines do actually work. What have you got here? You've got medicines that can take people who are sick or are going to be sick fairly soon, and that just no longer happens. They're not sick anymore. They're never sick. What does this mean? Well, first thing it means is you don't have to give them all the medicines that you would have had to give them if they were sick. You're only giving the preventative stuff. And yes, that costs money too, but we all know prevention is better than cure. And better often means economically better. Second thing is, the kids of the elderly are going to be more productive because they're not having to look after their sick parents. And the third and biggest thing of all is, the elderly themselves are going to be able-bodied still. They're going to be in a position to continue to contribute wealth to society. So the entire economy, the entire population is going to be enormously more prosperous if people have these therapies than if they don't. Putting it the other way around, it would be economically completely suicidal for any country, however ideologically screwed up, to deny these therapies to people on the basis of ability to pay. It would be suicidal. The only real precedent that we have today that can be applied, and it's not a particularly good one, but it's a hell of a lot better than today's high-tech medicine, is basic education. Basic education is free, even here. I mean, too basic, yes, but it's still free, right? Right? And the reason it's free is ultimately the same thing. if it were not, then 20 years down the road, you're going to be bankrupt. And because you wouldn't have an educated workforce. And there are very few people who are arguing, and they don't get many votes, for basic education not to be universally free. So that is the right precedent to be looking at right now. Now, of course, there's a whole bunch of other corollaries of all of that. For example, how would the medical industry work? The medical industry today runs entirely, or very largely, on keeping sick people alive, right? So it sounds like this would completely destroy their business model. But that is very short-sighted. That's not really true. At the end of the day, making medicine that's preventative is the same business, involves the same skills as making medicine that's treatment. You know, the reason it's the same companies that make most medicines also make statins. They also make ACE inhibitors. You know, these are preventative medicines. And that's an easy shift to make. As and when public opinion and public policy shifts in a more preventative direction in regard to the health problems of old age, because it can, because the therapies have been developed. As and when that occurs, the medical industry will simply follow the money, and they will do so perfectly willingly.
From the first moment that I can get your rejuvenation therapy to the moment that the poorest people in the world can get rejuvenation therapy, how long is that?
About a week. I mean, really. The thing is, people are going to be ready. This is what I was saying earlier about me being really, desperate to talk to policymakers and opinion formers. The shift of public opinion is going to be seismic, and it's going to be extraordinarily sudden, but whether or not that shift is as turbulent as it's in danger of being, it will predate the arrival of the medicines by at least a decade. And that means that one way or another, turbulent or otherwise, it will have all shaken down by the time the medicines come along. So for sure and certain, the medicines will be available to everybody pretty much the day that they're available to anybody.
Can I ask my question now?
Yes.
I'm here. To elaborate on the last question, I respectfully disagree with you. We've known about social determinants of health since 1977. We've known about the impact that education has on healthcare. And I just keep thinking that this is going to be viewed as experimental. Health insurance companies are not going to cover this, and it's going to be a modern day version of the purge, where it's only the wealthy that will have access to this. And I just simply do not see how 1 week time is going to allow people that don't have the resources to have this. We're seeing time and time again the health inequities that are happening in our country with race and poverty. It's everywhere. And here in San Francisco, we see it on the streets, and I don't understand how that model works.
So maybe there are some parts of what I said that you didn't get. I was not talking about 1 week. I was talking about 2 particular weeks, 10 years apart or more. The week in which people get the idea that this is going to happen, and the week in which it becomes available, right? But you're quite right. I mean, I'm certainly not trying to say that suddenly society will become more egalitarian across the board. Absolutely not. I'm quite sure that's not going to happen. But at the end of the day, we've got to look at various levels of this, of the motivations, of the drivers. There is the humanitarian level, which I'm not regarding as dominant, because ultimately the lack of humanitarian thinking is precisely what drives the lack of universality of access of anything, right? There's the electoral level, that is, like it or not, we do have egalitarianism when it comes to number of votes. Poor people have the same number of votes as Bill Gates. And at the most important level is the pure mercenary economic point, the fact of prosperity. Now, some prominent politicians these days make some pretty bad mistakes when it comes to that kind of thing. But the fact is that there's only so many mistakes you can make before you no longer get elected. And the there's going to be this time to think it through, to shake it down. Not to think it through, but debate it, where the merits, just economic merits of making these things available will be debated and discussed. And even to the extent that electoral imperative can be discounted, which I don't think it can, the economic imperative to ensure that one is making these things as available to everybody who's old enough to need them as other countries are will be completely irresistible.
Right here.
Thank you. You've had a lot to say about big picture. When this all works out really well, this is how our society will grasp it. Maybe because I'm a physician myself, I treat a lot of people who are younger than 50. I treat women with breast cancer who are in their 30s, and I hopefully, for the most part, are actually helping them beat their cancer. Disease isn't just for people over 50.
Sure.
It would help me as a skeptic to a lot of what you've said. I'm not curmudgeonly, but it would help me to hear a few more specifics, something that's tangible as to what you really are doing right now. I understand that there are some great companies that are potentially about to put something into trials, but if you could just give some more specifics to help me trust you.
Yeah, okay. So
it would be great.
So I occasionally get invited to speak at medical conferences whose audience is mainly MDs, and I often find it quite difficult because, with the best way in the world, MDs, have their hands full with the stuff that is already available, and they'll worry about stuff that's coming down the pike when it comes down the pike. So it's not often the most attentive audience to what I have to say. But I mean, you understand, I'm sure. But you understand, I'm sure, that essentially, everything that you prescribe to anybody came from research. It has to. There's a process there, and I'm, at the early stage of that process. So I'm needed in the long run. The question is, are the kinds of things that people like me are developing, are they likely to deliver the kind of promise that I'm describing? That's essentially your question. Now, of course, we don't know the time frames. As I mentioned earlier in response to your question at the beginning, the time frame for developing all of this to the point of availability is, I feel I have a responsibility to give a 50-50 prediction of 20 years, but I always couch that in the context of the fact that it could be 100 years with at least 10% probability. Sure. Now, in terms of specifics, well, I mean, of course, I did talk about a few of the examples, especially these cases of, augmenting the catabolic capacity of cells by introducing enzymes from bacteria. This is something that we've done very well with. We've done a bunch of immunotherapy against amyloidosis in the heart. We actually, as I think I mentioned, don't do much stem cell therapy because we don't need to, because all the important things are being done by other people. There's, I think, 3 or 4 stem cell therapies for Parkinson's disease happening right now. That's probably the kind of poster child of an aspect of aging that is mainly driven by cell loss. So, it's very important as a proof of concept for the broader category, and so on. I mean, I could go on as much as you like, but yeah, I mean, we're not short of specifics. I think really the only basis for any skepticism is the fact that these are early stage, and obviously the reason why there is a clinical trial process is because things do fail at each stage of clinical trials. So we don't know what's going to happen. But if anything gets even, to the beginning of the clinical trial process, that certainly means that the concept has a lot of validity in the lab.
I think part of it is it feels like maybe there was something missing that wasn't being said. Like really, it is there, we're there, but I think what you're saying is we're not. That you have great hope and you have great ideas.
Well, it's much more than hope. It's the same it's the same level of expectation, cautious but realistic expectation that any researcher would have. Yes, it's a very broad.
Big step.
Well, it's not just one big step, that's the point. It's a whole bunch of relatively small steps. Each individual component of this is just like any other research program in medicine. It shouldn't be viewed as qualitatively different, because it just isn't. The only thing that is qualitatively different is the juxtaposition, the union of these things that will give rise to something that is much bigger than the sum of its parts.
That to me is very clear, and I appreciate that.
Let's come, yeah, you had your hand first, and then we'll come up here.
Thanks. I am not a physician, but I do date one. And I have been, just in some of the podcasts that I listened to, I've been noticing a bit of talk about rapamycin and the inhibition of mTOR, and I'm wondering if you could talk, just wondering what your thoughts are on that, and sort of any sort of small molecule strategy that I may have missed when I was looking at your talks, but it didn't seem to figure into the 7 strategies.
Sure, okay. So first of all, it's rapamycin, not rapamycin. That's something, that's one of my little pet peeves, because people get that wrong a lot. Yeah, you're right. Small molecules don't feature a great deal in what I say and what we do. And the reason for that is because they basically don't seem to be very promising in terms of making big differences to what how long we can live. Specifically, the reason they don't is because they don't do rejuvenation. They don't do damage repair. They do slowing down the creation of damage. Rapamycin is probably the best of the classical examples of what are often called calorie restriction mimetics. So these are molecules that essentially trick the body into thinking that it's not getting enough calories when it is. Now, it's been known since the 1930s that if a mouse or a rat actually doesn't get as many calories as it would like, then it lives longer than normal. Quite a lot longer, like 30 or 40% longer, which is awesome. And sure enough, it's been a very well-studied phenomenon ever since.
Caloric restriction.
Yep.
Yay.
That's what it's called.
Intermittent fasting.
Yeah. Unfortunately, it has been very obvious, though it has been scandalously swept under the carpet by people who fund their own each other's grant applications. It has been very obvious for a very, very long time that longer-lived species acquire less benefit from calorie restriction than shorter-lived species. If you're a really short-lived species, like a nematode worm, you can multiply your lifespan by a factor of like 5 by calorie restriction done just right. You can't do that if you're a mouse. You can get 1.5, 1.4, something like that. That's pretty damn good. I'd take that. Unfortunately, we're not mice either. Dogs, people have done that, 10%. Monkeys, a couple of percent if you're lucky, not good. Furthermore, this actually makes evolutionary sense. It's fairly straightforward to explain why this correlation would exist, this inverse correlation, simply on the basis that long famines in the real world, in nature, are much less common than short famines. So the selective pressure is less. But what does this mean? What does it mean for drugs like rapamycin? Well, unfortunately, it means quite a lot, because what it means to be a mimetic is that you activate the same genetic pathways, the same gene expression changes that would occur in the context of the real thing, which means that there is no way in hell, and nobody would dispute this, there is no way in hell that a calorie restriction mimetic will ever be able to elicit a stronger response than the real thing, calorie restriction itself. And since that response in humans is tiny, if anything, I mean, obviously the clinical trial hasn't been done, but in monkeys it's definitely tiny, then, yeah, we can't really look for much. Now, I do want to qualify what I just said, because the fact is, calorie restriction, even in species, long-lived species that don't gain much in terms of lifespan, they do gain quite a bit in terms of healthy lifespan. It does kind of square the health curve. You stay healthy longer, you're kind of made more resilient to the slings and arrows of outrageous fortune. So that's probably true in humans as well. And for that reason, I am certainly very supportive of the efforts that have been made to develop drugs, including ones that people can make money out of, which they can't make out of rapamycin because it's a natural product, In this area. That's all great. What is important to me, though, is that people should not get an excessive idea of how much they can do. Again, it's a sense of proportion thing. This is not the Holy Grail. It is good for you, probably, but it is definitely not the ultimate solution.
Come up here with the mic. Oh, right up here. We got the mic coming right now. Awesome. Thank you.
Hi. I've been fascinated by the Mexican salamander that can regenerate itself. And I used to always wonder how, like, if you have an amphibian that gets his, hand cut off and it regrows.
Right.
It's very fascinating to me. Yeah, because every part of its body, because it's in an embryonic state.
Right. So gerontologists have paid a lot of attention to the regenerative capacity of lower animals for a long time, because that has been recognized that there's a lot of potential mechanistic overlap. At the end of the day, the human body only keeps going as long as it does because we have a lot of inbuilt mechanisms for damage repairing damage as it happens, so that it doesn't accumulate. So, one might kind of look at these as, two sides of the same coin, really, that the process of regeneration happens at the molecular level, at the cellular level, at the anatomical level, and maybe it's all part of the same thing. And sure enough, we do also find that lower animals can often live longer, depending on how you treat them, than you would expect. So, absolutely, it's a very important area, and the question is, can we exploit it? Well, probably. The second place I work, my primary affiliation, as you've heard, is SENS Research Foundation, this non-profit down in Mountain View. The other place I work part-time is Agex, which is a company based out in Alameda, run by a guy named Mike West, who's one of my big heroes in this field, really the pioneer of doing proper anti-aging work in the private sector. And our work in Agex is mainly focused on this kind of thing. We are interested in using stem cell therapies and other, stem cell stimulators to enhance regeneration in the context of aging. And a lot of the information that we base our work on does come from organisms like this. However, I do want to emphasize that there's an enormous amount that's not understood about this. We would love to be able to get our heads around it, but it's not just one gene the way telomerase was.
Yes, another question up here.
Sure.
1 second.
It's
One
coming.
moment. We have the mic coming.
As the man on the bleeding edge of anti-aging, what do you do personally?
I get this question more often than I would like. The fact is, you should do as I say, not as I do. For two reasons. Number one, I'm really well built. I'm just really lucky, whether genetically or epigenetically. I've been able to get tested, really high-end tests of my biological age over the past 15 years, 5 times now, I think, and I always come out ridiculously younger than I actually am.
And how old are you?
I'm 55. I seem to be able to eat and drink exactly what I like and nothing happens, and I don't even need to do much exercise, so that's pretty good. Which means, of course, that the way I live my life should not be a recommendation to people who are less lucky than me. The second thing is that because of my job, I end up getting far less sleep than I ought to have, and that's definitely bad for me.
Mm-hmm.
So, don't do that.
Yep, right back here, and we got a mic coming.
So I really appreciate your work.
Thank you.
Since the 90s, of course. I go back to the 80s and doing this stuff with pro athletes, Navy SEALs, internationally, work with doctors and doing fun stuff like that. And so I've been pulling my hair out for a long time trying to figure all this out. And so my question directed towards you is not too dissimilar from his, in that I spend most of my time in the fitness world fighting fad diets, 80% fat, 20% high quality protein, or vice versa. And I think we kind of have an understanding of their detrimental effects towards lipofuscin and protein carbonyls and superoxide dismutase and all these wonderful things that you talk about in your books and that we understand in research. So how would you explain what an optimal diet would be for humans?
Yeah. All right, so I'm going to put this in very simple terms because I don't know how much expertise there is in the audience. A lot of people think that diet matters a lot in aging. And they think it for reasons that are both true and not true. And the reason they have this kind of, Schrodinger kind of opinion is that they're oversimplifying the question. For sure, and this sounds like it's very much part of your professional life, it's very easy to shorten one's life quite significantly by a really bad lifestyle, including diet. But that's not really relevant here. We should not be dividing the population into two categories, the people who do things right and the people who do things wrong. Instead, what we should be doing is dividing them into three categories. People who do things wrong, people who do things the way their mother said, but that's all they care about. They don't try and look out for anything clever. And people who really pay attention to the, they do their very best to, to get the extreme. The reason it's important to divide it into those three categories is because the difference between the bad category and the what your mum said category is quite large. Whereas it seems that the difference between the what your mum said category and the optimum category is tiny. When I was talking about the impact, the benefit of calorie restriction across species, that was what I was talking about. In the early 2010s, about 5 years ago, there were two very important studies published, which were reports on studies that had been going on for more than 20 years on calorie restriction in monkeys. And to a large extent, the studies were replicates of each other. They were done in the same kind of species of monkey, and there were differences in terms of like the range of ages of the monkeys and so on, but not very much. And they were both nice, large studies done by very, very, very reputable people with lots of money, obviously. And they got ostensibly rather different results. Essentially, if you just read the headlines, one of the studies said calorie restriction works and the other one said it doesn't. But if you looked closely, it was all about what I was just saying. Because it turned out that the study where it looked as though it worked was using a rather poor diet for the, of course, the calorie restriction is all about the quantity of food, not the composition, right? So, of course, in both experiments, the composition of food with the controls versus the restricted animals was the same. It was just that the quantity was different. But in one study, the food that was used was a rather refined, not terribly good diet. In the other study, it was much more like what you would have recommended. And sure enough, the study where it was what you would have recommended, it was the one in which calorie restriction didn't work. The one in which the diet was made of bad stuff, the controls, were rather more diabetic and such like. So so it was the conclusion that was come to was that actually that was a large part of the explanation for the disparity in the headline results. There was more than that. There was also the fact that actually the controls in the study where it didn't work were slightly restricted. So we decided like there was an added confounder. And if you look at all this, you had complete 20/20 hindsight, you would say, what the fuck? Why do they do the experiment so badly? But you can say that about absolutely every scientific experiment that's ever been done, because the fact is, that's why we do experiments. Einstein said, if we understood what we were doing, it wouldn't be called research. So you absolutely cannot blame the experimenters. No, they just were learning as they went along. But the fact is, that's probably the single best experimental example of what I'm saying, that you have to, consider what the kind of default middle ground is of just doing what your mum said.
Another question back here. The mic's right behind you.
Yeah. Can you say more about the clinical trials, like what they are, what exactly is happening with humans and where?
Okay, yeah. So at the moment, out of the 7 types of treatment that I think we're going to need for the comprehensive defeat of aging, most are not yet in clinical trials. The one that's been moving towards clinical trials the most rapidly across the board is undoubtedly stem cell therapy. And the work that's going on in Parkinson's disease is probably the furthest along. The first attempt to use stem cells against Parkinson's was done more than 25 years ago now. And it was done at a point where we really didn't know bugger all about how to do stem cell therapies. And so sure enough, it didn't work very well. But it worked well enough, occasionally, just by kind of fluke really, that it inspired people to go further eventually. And now we know so much more about how to control what we're doing with stem cell therapy. Everyone's very much more optimistic. So as I said, there are several trials going on right now. There are other trials going on in stem cell therapies for other things, but that's really the one you should be paying attention to because it's the one that's most classically, a damage repair approach. Very often with stem cells, what you're doing is not actually the sense thing. You're not actually trying to replace the cells that the body is failing to replace. Rather, you're introducing stem cells that will secrete stuff that will be generally, give a good vibe to the cells around them, which is kind of not the same. The next one that's gone a long way is getting rid of molecular garbage. I mentioned this earlier on, but the molecular garbage where things have gone furthest in the clinic is actually garbage outside the cell, which we classify as a separate category. And the reason we do so is because it is treated in a different way. The way you treat this stuff is you just basically, you cause the immune system to engulf it. And that works because once it's inside cells, then it gets destroyed much more easily. There are variations on that theme, but that's the essential idea. And that's now completely done. People have figured out ways to use the immune system to eliminate this stuff. It's called amyloid. You've probably heard of amyloid in the brain in Alzheimer's disease. There are other types of amyloid in other organs in different aspects of aging. We know how to do that now. Now, in Alzheimer's disease, the results in terms of clinical intervention have been rather underwhelming. In fact, they've been basically zero. But we should not be surprised by that at all, nor indeed discouraged, because Alzheimer's, of course, is a very complicated disease with many other factors in addition to amyloid. So, as with the rest of aging, you would expect to have to fix everything in order to see a big effect. And we can only fix that so far. But that's a good start. Then in terms of other stuff, well, so senescent cells, so cells that get into a state where they are secreting toxic stuff, they're doing more harm than good, and the body would like to get rid of them, but for whatever reason they are resisting the body's effort to kill them off. So drugs have been developed now that are the first step towards getting rid of these cells. They don't work all that well, but they work well enough that the company that's spearheading them is now valued at over $1 billion. Unity Biotechnology, based over here in San Francisco. And other companies are coming along trying to do things in a slightly more sophisticated way. Again, clinical trials, going to happen this year, so I'm told. That's the word on the streets. The stuff I mentioned about macular degeneration for eliminating the garbage that kills the cells at the back of the retina. That is, again, going to be in clinical trials within a year. That's one of our spin-outs. So yeah, I mean, it's all going pretty well.
Good.
I'm sorry?
With the heart.
Heart, well, where shall I start? Okay, there's loads of things that go wrong with the heart in old age. First of all, there's atherosclerosis. So that's the accumulation of fatty deposits in the artery, in the walls of the major arteries. That's actually something I did mention earlier, and yeah, it's close to clinical trials. This idea of using bacterial enzymes to eliminate the oxidized cholesterol, again, it's moving along pretty much in the same way that the macular degeneration one is, and I believe it's, I think, yeah, a year or two maximum from clinical trials. Then another thing that goes wrong with arteriosclerosis, the stiffening of the arteries caused by molecular changes that happen to the extracellular matrix, this lattice of proteins that gives the arteries their elasticity. So that's something that, again, we have made a huge breakthrough in, work that we funded at Yale University. That's just moving into the private sector right now. It's going to be our next spin-out in the next month or two. And I think that's also getting fairly close. We've got very good candidate enzymes. I would say probably another year or two in addition, so maybe 3 or 4 years out. But yeah, we're definitely getting there. Then there's amyloidosis. So this one's quite big. So we could be getting there within a year or two. This is, again, some work that we funded. So I just mentioned amyloid in the brain, where it's already been done. It's been through phase 3 clinical trials. Everybody has established it can be done. We funded the development of a use of a rather different way of using the immune system to get rid of amyloid, which essentially involves antibodies that chop up the amyloid rather than just engulfing it. And that works really well. We published a proof of concept paper 4 years ago now. That's also been spun out into a company, and it really ought to be in clinical trials within a couple of years. There are other approaches to getting rid of this amyloid, which in the heart, which are already in clinical trials. I don't think they're going to work so well, but again, that's working well. And then the final type of heart problem that people often neglect, which is something I really want to have worked on, and I haven't been able to make this happen yet, but again, it ought to happen soon, is a stem cell thing. So there's a particular type of cell in the heart called a pacemaker cell, which is involved in essentially communicating the signal from the brain to the heart that says, please beat. And if you're extraordinarily old and nothing else has gone wrong with your heart, it stops anyway, because these cells die off, they're not replaced, and eventually the brain is just, can't get the signal through to say, please beat. So we want to replace those cells. Again, it's something that really ought to be pretty straightforward. It's just stem cell therapy.
All right, that was a very solid and diverse Q&A session as well. Really great stuff.
Hey, we've got another 10 minutes.
Yeah. Well,
there's another question.
Yes, we'll wrap up, and then you guys can ask Aubrey questions for the last couple of minutes before he has to bounce. I want to thank the Battery and thank you all for coming out. This has been really fun. Did you guys have a good time? Yeah? Awesome. You can reach out to Aubrey. Aubrey's Aubrey at SENS.org, SENS.org. Also, you can follow Simulation, simulationseries.com. You can find our live events there, as well as all of our other multidisciplinary videos that we host. Thanks for coming out, and stick around and chat a little more. Thank you. Thank you.